Welcome to today's episode of Researcher Live, a webinar series dedicated to helping researchers stay up to date on the latest advancements in research technology and methods. Today, we'll be discussing how artificial intelligence is transforming knowledge discovery. We've gathered a panel of experts who share their knowledge and expertise with AI. In addition, they will discuss how generative AI, including large language models, much like ChatGPT, and how it's likely to replace or complement these technologies. Before we officially present our expert panelists, I just have a few housekeeping items. You are all in listen mode, so you don't have to worry about any background noise or your cameras. If you have a question, we do have live Q&A enabled. On the Zoom bar below, you'll just click Q&A, and as the conversation goes, you can submit your questions. We'll have time at the webinar to answer those questions, so we highly encourage you to share. And then lastly, if you want to review the webinar or you want to share it afterwards with colleagues, we'll be sending the recording right to your inbox a couple of hours after the webinar is over. And so our panelists today are Chris Bendall, Director of Product Strategy here at Research Solutions, and Enrico Motta, Professor of Knowledge Technologies at the Knowledge Media Institute. KMI is a multidisciplinary R&I lab at the forefront of innovation for the last 20 years. So welcome, Enrico and Chris. And my name is Lydia Lindenberg. I am the Senior Content Marketing Manager here at Research Solutions, and I shall be your moderator for today. And so quickly, we have a brief overview of Research Solutions for those of you who may not be familiar with us yet. Founded in 2006, Research Solutions provides solutions that simplify and streamline how organizations discover, acquire, and manage scientific articles and data. More than 70% of the world's top pharmaceutical companies, emerging life science firms, and other R&D-driven companies rely on us for one-click access to scientific literature. And now, before I hand it to our panelists to dive right in, I'd love to know more about your experience and thoughts about today's topic and the AI landscape. So we'll start with our first question. What do you think about artificial intelligence in knowledge discovery? The options are, I'm excited about its potential. I'm concerned about its implications. I don't know enough to form an opinion, or other, which can be specified in the chat. And our second question, what is your experience using artificial intelligence in knowledge discovery? I have significant experience with AI and knowledge discovery. I have some experience with AI and knowledge discovery. I'm aware of the potential of AI to aid in knowledge discovery, but do not yet have any experience with it, or I'm not familiar with how AI can be used for knowledge discovery. All right, we've got our results in. It seems like there's a lot of excitement around the technology, which is very exciting. All the more reason we're excited to dive in today. And it looks like there's some experience with AI, not a lot of significant experience. So this is a perfect topic to be delving in a little bit more deeply on. So exciting stuff. Thank you all for sharing. And with that being said, I'll hand it over to our presenters.
And also a very warm welcome, myself and Enrico. And yeah, it's great to see that you're excited about this topic. It's great to see also that, yeah, there's things you would like to learn. We're going to be showing you various examples and potential solutions for looking at different use cases in knowledge discovery. A lot of the examples, most of them are projects and things that Enrico and his team from the Knowledge Media Institute at the Open University in the UK have been working on. I mentioned the term solutions just now, and when thinking about solutions, of course, we are solving a problem or a challenge. And in this case, broadly, it's the challenge of information overload. So I was thinking about how to define this challenge. And as with most of us probably increasingly are doing these days, I turned to ChatGPT to help me summarize what information overload potentially means. And it said, information overload in scientific research refers to the overwhelming abundance of data, literature, and research findings available to researchers. It can hinder their ability to effectively process and synthesize information, leading to difficulties in identifying relevant and reliable sources, making informed decisions, and keeping up with the latest advancements in their field. So that is one definition, broad definition of information overload. A way of illustrating that is probably a fairly well-known, the exponential growth of scientific research articles. So this curve illustrated on the left here. So we are publishing more and more all the time, vital, critical, peer-reviewed information that scientific researchers in academia, but also in corporate research, need to search through, access, and extract information from to help them in their own research. When we think about scientific research, and also especially corporate research, it's not just about scientific journal articles, it's also about a very broad array of different data types, some of which are listed here on the right. And critically, it's not just about finding specific pieces of information or that one critical article that you need for your research. It's also about understanding the connections between topics, the connections between concepts, the connections between authors and collaborators. So a whole range of different, variety of different concepts, which this information, all these different information types include, and thinking about how they are related to each other, how are they connected, because it's these connections which are important to understand to further scientific research. And this is going to be a central topic of what we're talking about today. We also, as already highlighted, will be addressing the topic of generative AI, so ChatGPT, for instance, which is definitely part of the solution to the challenge of information overload, but potentially also going to be one, also increasing the challenge of information overload. We've seen, I think most of us have used generative AI now to, create first drafts of documents. In the next year or two, it will greatly improve the way scientific researchers are, for instance, able to create journal articles from their research. And so increasing the time to publication, increasing the success of their manuscripts in going through the publication process. So generative AI, definitely part of the solution, but also, we'll see that this information overload issue will gain in velocity in the next years as well because of it. Today, we're going to be talking about knowledge discovery, but we're going to be talking about some specific use cases within the broad topic of knowledge discovery. There are many, many, many different use cases that you and I are dealing with on a daily basis in trying to find information for the work that we're doing. These are just a small selection of the vast array of use cases that there are. Some of them particularly relevant for corporate innovation in particular. Today, we're going to focus on the ones highlighted in white, focused on search and discovery for topical analysis, trend analysis, prediction, and hypothesis generation. Another important message or idea that we want to bring across in today's webinar is that AI is being used in a lot of different ways to create knowledge discovery systems. When we think about a knowledge discovery system, it's not just that end solution, the way you interact with information and get information back in different forms, so specific use case which are being addressed, but also the key foundational components of very good knowledge discovery systems such as taxonomies, ontologies, and knowledge graphs. And important here is to understand is that AI is used and leveraged in each step of creating these components, of creating these systems. The different types, so AI is a very broad term. The types of artificial intelligence technologies that we will refer mostly to today are natural language processing, machine learning, which includes deep learning and neural networks, and closely related to that, large language models as well, so generative AI. All right, so with that, we're going to focus in, first of all, an example around the first component, ontologies, and the work that Enrico and his team have been doing at KMI on a computer science ontology. Enrico, tell us about this.
Yeah, thanks for bringing me in, Chris. So basically, this interesting work, because it's one of the very first things that we start doing when we start this area of research, which is now over 10 years ago. And basically, what the motivation was that, at the time I was editor-in-chief of a journal, and also, of course, I was a researcher, but also a research leader, and sometimes I was involved also in strategic panels to do with funding bodies, so with the research communities. And basically, it kind of occurred to me that we were constantly sort of giving advice and making decisions on the basis of relatively little information, in the sense that we didn't really have very detailed intelligence about what was going on in research, in particular in computer science, which was my area. And in particular, for example, we didn't have even a detailed map of what kind of research was going on in computer science at the time. We, of course, had high-level concepts and areas like artificial intelligence, but we couldn't really separate, understand, for example, at the fine-grained level, which communities within artificial intelligence were becoming more important, which communities were publishing more, were publishing less. And for example, if a particular area of research was going down, an interesting question was, okay, those researchers who were working in these areas, what are they doing now? What is the next, big things coming up? So basically what we did was, okay, we realized that we needed to have a way to generate these very granular maps of a big research field like computer science. And then, of course, as a next step, to be able to use these very granular maps to classify precisely computer science papers, so that we could do then this very fine-grained analysis about which research areas are becoming important, which research areas are becoming less important, which trends concern industry and academia, etc. So the first step was to develop this system ontology, which comprised about 14,000 research topics, 10,000 of which come under the broader heading of computer science. So it's a very, very granular taxonomy of research areas in computer science. And then with my team, we worked on a classifier, basically a computer program that, given a paper, a scientific paper in computer science, is able to produce automatically the research areas within computer science that are relevant to this paper. And I'm not going to go into too many details about the classifier, except pointing out that basically is a combination of various reasoning modules. Of course, if a paper talks a lot, uses a lot the word, for example, artificial intelligence, there is a very good chance that that paper, is talking about artificial intelligence. So there is a rather simple syntactic module that looks for occurrences of research topics in the paper. But then there are slightly more complicated things based on what we call the semantic module, basically essentially on word embeddings to identify also topics that may not be explicitly mentioned in the paper or may be expressed in a way which is syntactically different from the normal way. And then we do further post-processing to essentially reduce the number of false positive and come up with a compact and correct number of topics. And one thing I would like to point out, the system classifier is freely available online. So if people are interested, they can, search for CSO classifier. They go on to our website, SKM website, and they can try classify their papers. And then, of course, we will be very happy to receive feedback about whether our classifier is better than manual annotation.
Right. So with the classifier, leveraging the ontology and then the classifier, you're then able to, classify all these different articles, scientific reports, courses, to be actually define what these different artifacts are talking about, the topics they're talking about. And that brings us then to one of our other main or first use cases, which is then leveraging this information for trend analysis.
Exactly, and this is just one particular example of the many opportunities for essentially large-scale research analytics that the computer science ontology opens up. So the moment now, given each scientific paper, we know exactly, not only the traditional metadata, who is the author, which organization the author is affiliated with, the publication venue where it's been published, the date of publication, etc. But we also know precisely which areas are being tagged by the paper. And of course, we don't need to limit ourselves only to scientific papers, but we can extend our analysis to commercial patents. And so basically, as shown in this diagram, we get this kind of two-dimensional space in which we can look at patents versus papers, but also industry versus academia. And then we can start doing some interesting things. For example, we can start looking at, okay, what are the main shifts, for example, that have happened in the past 5 years? This analysis from 2018. So when we talk about 5 years, we'll be talking about 2013 to 2018. And we can look, for example, which areas which started as important scientific areas have had a particularly significant impact in the past few years in industry. And in particular, for example, we can, as shown in the first table on the top left corner there, we can look at the main shift from essentially the scientific landscape to the commercial landscape, the one for patents. But also, for example, we can look at the other way around. As shown in the slide, pretty much 90% of research topics first emerge in academia. But there is, a percentage, about 10%, will actually emerge first in industry. And indeed, it's interesting that while the gap from academia to industry is on average about 6.5 years to industrial patents, academia actually tends to be very receptive to new ideas from industry. Pretty much almost automatically, new ideas from industry are taken up by academia. And for example, the table on there shows some of the topics that originally were primarily focused for industry, but by 2018 it became major academic fields of inquiry, for example, like the Internet of Things that, of course, exploded in those years.
Right, and then you can take these type of analysis of trends and then, build machine learning systems which can then look at this information and start to forecast, to predict based on this trend analysis, the types of topics which will be very important for industry in the future.
Exactly. That's where things start to get more exciting. That we not only need to do analyses that are kind of historical, but then we can also start to make predictions. And indeed, yeah, we did some experiments, and we found that we could basically build a neural network forecaster that was pretty good in given the current state of research, of scientific research in as shown by the current publications. We could predict pretty well which of these scientific topics will be most likely to really have a serious impact in industry. And of course, this kind of intelligence is extremely valuable, not just to industry, but also to academia, but also to funding bodies, governments, and other kind of organizations.
So here we've mostly been looking at actually the topics, looking at the trends and how topics are rising, becoming more interesting. But there are other other concepts, entities within the metadata that we can also use to also enhance these predictive models. And this is work, I believe, that you did sort of modeling based on the emergence of semantic search in the early 2000s. And what are some of these other concepts, other entities that you're using then to enhance these predictive models? Yeah,
this was really fun work that we did a few years ago with a really excellent PhD student, Angelo Salatino. And essentially, once we started collecting all this data, we started analyzing and annotating millions of papers. We thought, well, as I said earlier, in addition to historical analysis, can we also start predicting what's going to happen in the future? And in particular, if you talk about people who have studied the evolution of science, they will talk about these sort of revolutions, like a cool paradigms, the way suddenly something new emerges in science that is changes completely the landscape of what kind of research people do. So basically, as shown in the picture, the analogy we use is like a volcano. I'm not a volcanologist, so I don't have direct experience or expertise, but I understand that volcanologists can detect pretty well the signals coming from the volcano that are indicators of a future eruption. So basically what we did is that we looked at these network of collaborations between authors. We looked at the network, at the relation between topics, which topics are more distant in the network constructed by annotating millions of papers, which topics are more distant. And then we were able to identify changes in the network. For example, authors that seem to belong to different communities, they start to collaborate, in particular influential authors, or authors that start to working on research areas which are much closer than they used to be. And basically, with a lot of, I would say, computational hard work, we eventually were able to understand these sort of topological fingerprints that were correlated with the emergence of new areas. So, for example, this particular example is to do with the emergence of semantic search as a research topic in the early 20s. Google basically exploded around 1998, 1999, and as usually as academics do, they immediately picked up, hey, there is something really revolutionary here in the way the Google algorithm works. Can we do better, for example, by adding more semantics, more understanding of what kind of concept we are looking for? And that basically meant that new papers came out and new authors started to collaborate at the intersectional areas such as World Wide Web and search engines, but also formal query languages that will allow to introduce this formal semantic element and with the aim of improving the quality of search engines. And of course, because these areas, semantic search as a research topic, didn't really emerge as an explicit area with a label until 1 or 2 years later. Of course, our prediction engine doesn't tell you the name of the new research area. It tells you, hey, there is something really interesting going on here. If you want to know more, it has to do with these areas, World Wide Web, query language, blah, blah. And these are the people and the papers you might want to have a look at, because maybe something really interesting for you is happening there in that space.
So these use cases we've been looking at predicting, looking at trend analysis, predicting future research topics. This has been possible by mining information mostly found within the metadata of journal articles. But of course, there's a lot of other information that we can extract from journal articles. We start data mining the full text of journal articles and all the concepts and relationships between concepts that they contain. We are then able to start addressing a lot of other use cases in knowledge discovery. So please, tell us a little bit about the power and the abilities of knowledge graphs.
Yeah, so basically, in a sense, you can see all this effort I've been talking about as an effort of going from scientific publications and other documents, which is essentially text, to extracting exactly the kind of ideas and the kind of concepts that are important for scientific research that are expressed in these texts. So earlier I showed you that if we can classify papers precisely according to the fine-grained scientific area, then we can do all sorts of interesting analysis. Of course, a paper is not just about being in cybersecurity or semantic web or artificial intelligence. A paper typically tackles a particular problem, a task, using a particular approach based on some method or some technique, etc., evaluates on particular benchmarks using particular metrics, etc. So essentially, the next step, which is exactly what we are working on right now, is to try and extract automatically all this information from large collections of papers. Again, we are talking about millions of papers. Formalize it into a knowledge graph. This is essentially a structured representation, a little bit like shown in this diagram here, in which essentially you know exactly this paper talks about this task, which is being tackled using this method and is evaluated using this metric. So we put all this information in a structured database called knowledge graph. And then again, this opens up a lot of opportunities to try and do interesting analysis that can support scientific research.
Right, because once you have all this information represented in a knowledge graph, then you're able to basically ask questions of the knowledge graph for a huge variety of different use cases, because you have all these different types of concepts which have been annotated and understood, and the relationships between them as well, which really opens up an enormous range of ways that we can interrogate these knowledge graphs to answer questions that we have and actually generate hypotheses as well for the research that we want to do. Here is an example of a knowledge graph which has been applied to drug repurposing. So this was from an article published in July 2020. So it's focused on trying to understand what existing drugs could be used as therapies for COVID-19. So just within the first 6 months or so of the pandemic, the authors were able to create this knowledge graph, which was looking at 39 types of relationships between drugs, diseases, proteins, pathways, and expressions, which they had extracted from 24 million PubMed articles. And once they had this extracted this to the knowledge graph, they were then able to ask the question, which existing drugs potentially could be used as therapies to treat COVID-19. And the knowledge graph was able to deliver a list of 41 existing drugs, so a short list of drugs, hypotheses of which existing drugs could be used to treat COVID-19. And in subsequent research and in clinical trials, the efficacy of these drugs was also validated. So this is one example of the types of questions that we can ask knowledge graphs and the types of insights that they allow us to find. And we want to build on this topic of hypothesis generation with some new work which Enrico and his team have been doing, not only leveraging knowledge graphs for hypothesis generation, but also now combining it with the power of generative AI.
Yes, indeed, this is work going on kind of today. So these are still very preliminary results. But essentially, the idea is, as you were saying, Chris, is that once we are able to extract all this information from a vast corpus of scientific papers, and we formalize it in knowledge graph using these concept, task, methods, etc., then we can look at the knowledge graph for new scientific hypotheses, or let's say for new research hypotheses. That is, are there, for example, relations between methods and tasks that have not yet been explored, but are plausible? And this is essentially the work that is going on hypothesis generation, in which essentially we use a kind of link prediction method to try and generate new candidates. And here we have one example on the right-hand side of the screen that is is an example of an hypothesis being generated automatically from analyzing our big knowledge graph. That is, for example, that to sort of use methods from sentiment analysis or gesture recognition or emotion recognition as a way to detect cardiac arrhythmia could be a very promising avenue. And for those who are not like me, who are not expert on cardiac arrhythmia, essentially the idea is very simple. There are, if you want to really diagnose this kind of conditions rigorously, of course, you need to use specialized medical equipment. But of course, if somebody has cardiac arrhythmia, there can be other signs, external signs, external indicators that could be picked up, for example, by system trained on emotion recognition or activity recognition. Because, for example, there are changes in activity, there are certain activities are impaired. So essentially, the idea is exactly this one. We are building a system that automatically generates these hypotheses, and then actually, because these hypotheses are produced as in this rather unfriendly format of triples, like the one showed on the right-hand side of the screen, we basically we use GPT to make them a little bit user-friendly, and in fact, essentially the user-friendly description of these triples has been generated automatically by GPT, which basically say, well, I mean, it would be interesting to see whether we could use multimodal biosignal analysis techniques to try and improve the diagnosis and treatment of cardiac arrhythmia. In fact, in particular, to improve the early diagnosis. You can see that the GPT could be a little bit even more intelligent. Say, well, we are talking about the early diagnosis. We are talking about diagnosing these things before these things become so bad that then rigorous tests are carried out. And of course, we can do even more. We can actually ask GPT to produce the research plans, because of course, if we generate an hypothesis, then we want actually to go about and prove it. And again, these are really they are no more than experiments. These are really experiments that have been carried out in recent weeks. But again, GPT seems to be pretty good actually at generating a research plan that makes sense for the kind of hypothesis that might be worth testing, in particular in this case, cardiac arrhythmia. And so this is actually relates to what you were saying earlier. That is, we can take advantages of all these new developments in AI to try and speed up the process. So nobody is here saying that our method, for example, for generating hypothesis is going to replace the creativity of researchers. Of course, at the end of the day, people who generate hypotheses carry out the research here. But what we can do is that we can develop tools that assist people and say, hey, from analyzing the literature on certain types of medical conditions, it looks like there's space to analyze whether this kind of multimodal biosignal techniques are useful in the context of cardiac arrhythmia. And then the researcher can say, well, actually, this is not a bad idea. Let's start exploring or say, well, this is a completely stupid idea. Can you suggest something else? That's the way this technology should be used.
Yeah. So we're going to look a little bit more on this topic of kind of hybrid AI. So bringing together, really revolutionary technologies like GPT, but combining it with, extremely well curated and sort of factual knowledge graph components to create knowledge discovery systems, which are, very powerful, very easy to use, but also critically to be transparent and traceable. So AI systems which adhere to the evolving, for instance, EU regulations, which are evolving, and one of the key components of those regulations is that AI systems, the results that they bring out need to be traceable and transparent. And I think these are examples of sort of recent research, which is around hybrid AI, or also known as retrieval augmented generation.
Yeah, indeed. As this example show, this is a very, very sort of hot topic at the moment. I think in the past few years, with technologies like deep learning first, and now with generative AI, have brought really unbelievable breakthroughs in the ability of AI system to perform tasks at an extremely high level. That only a few years ago people would not have predicted ChatGPT could come up with the kind of sort of analysis and textual synthesis that is able to do. But at the same time, I think people are starting to understand that, and people include also regulatory bodies like the European Union and governments around the world, that you can't deploy this AI system in a blind way on decision-making tasks, on decision support tasks, without them being able to explain what's going on. So essentially here there are two aspects. If you bring what traditionally is called knowledge engineering, if you bring this explicit representation knowledge like the one I showed in the knowledge graph earlier, then you can augment a traditional machine learning system trying to improve the exponential capabilities. But at the same time, we can also improve performance, because we can bring in essentially domain knowledge to remove some of the hallucinations that machine learning systems may be prone to.
Yeah, and so these hybrid systems are not only for creating those sort of complete the knowledge system, the knowledge discovery system, or addressing certain use cases, as we've shown, but actually also then using these hybrid AI methodologies to actually improve and create those components. So the ontologies, the taxonomies, but also using them to create knowledge graphs, as is shown here.
Exactly, and the details, of course, tend to vary from application to application, but the basic idea is very simple. If you try to understand phenomena such as the scientific literature, millions and millions of papers, typically you need the systems, like machine learning systems, data mining systems, large language models that can operate at these amazing scale efficiently, and in particular identify interesting regularities in this phenomena. But then, as we said earlier, if you want then to understand what are these patterns that emerge, for example, from this large scale analysis, you need to bring additional knowledge. So, for example, the very first example I gave today when we talked about the CSO ontology and the way we generated the research maps actually follow exactly the scheme shown in this slide. That is, we took 6 million papers in computer science. We did large-scale text mining, trying to identify in the text, to distinguish essentially in the text keywords that were associated with research areas from other terms, other keywords that were in the text. And of course, that gives you the ability to operate at scale. But then you need, before you publish the computer science ontology, you say, wait, this particular keyword I found in these 1,200 papers is actually denotes a research area called cybersecurity. You might want to bring external knowledge. So, for example, what is the external knowledge? For example, if you are unsure whether cybersecurity is or is not a research area, you get reassured from the fact that you bring a call for papers on cybersecurity, that people tag their research or the research, the web pages with cybersecurity, etc. So essentially, the idea is to augment the product of large-scale machine learning and data mining with explicit representational knowledge that can essentially provide additional evidence that some of the intuition or hypotheses that you have generated through large-scale text mining, for example, in this particular case of the computer science ontology, are correct. Indeed, we showed that the quality of the output increased dramatically. And we have used also in very, very different areas, for example, in robotic, in which we equip robots with additional domain knowledge so that they don't only rely on the perceptual component based on neural network to understand the objects around the world, but also they have a little bit of common sense. So, for example, they understand that although an armchair might look like a mug, typically a mug is much smaller than an armchair. So if you have common sense knowledge about the size of mugs and the size of armchairs, you are less likely to make mistakes in identifying these two types of objects. So it's a completely different domain, but essentially the pipeline is exactly the same, bringing domain knowledge to help explaining what's happening, but also improving performance.
Yeah, and thereby making the AI systems traceable, transparent, and more accurate. All right. Well, thank you very much, Enrico, for the insights to those various examples. This is our last slide of the webinar before the Q&A. And just to summarize, AI is used in various ways to help us create knowledge discovery systems. We've seen and been talking about technologies such as natural language processing, machine learning, and especially focused there at the end on large language models, generative AI, ChatGPT, and not only how these different technologies can be used to address specific use cases, but how they're also used to create and enhance the key components of a very good knowledge discovery system, which include ontologies, which include knowledge graphs as well. So thank you all very much for listening. And now we'll go into the Q&A. Just before that, Lydia?
Yes, thank you both, Chris and Enrico, for that awesome deep dive. I know I learned a lot, and I'm sure other folks did as well. Before we head into our Q&A, I do just want to cover a couple of quick bases. For those of you that aren't customers yet, and you're looking to access journal articles and book chapters quickly and cost effectively, I'd like to encourage you to go ahead and request a free trial with Research Solutions Article Galaxy. Learn how you can get up to 28% off your article spend and 86% of articles delivered within seconds. But that's actually not all. We are currently experimenting with ChatGPT for use within Article Galaxy as a part of our beta version. If you'd like to learn more about it or want to be a part of that beta version, fill out the form on the link and mention the ChatGPT beta in the comments section. I'll also include that link in the chat as well. And with that, we're ready to head into our Q&A. We've got some great questions coming in, guys, so thank you so much for your thoughts already. Why don't we go ahead and get started here? How can organizations leverage the power of AI in their knowledge discovery efforts?
Well, okay, I think we've shown a variety of examples of how they can do that. So I think the critical things that we're showing is that to have truly robust knowledge discovery systems, we need to have obviously access to data. We have to be able to curate and data mine that data, and we use then ontologies to help us do those tasks, and we use knowledge graphs to organize the information. And once we have these critical components in place, then there is a vast array of different use cases that we can address with these systems. And augmenting them, as we said at the end there, generative AI has a major role to play in the future. Anything you'd like to add, Enrico?
No, I think you covered this question.
Wonderful. Does AI replace human intelligence for knowledge discovery?
Should I answer this one?
Go for it, Enrico. Yeah.
Well, the quick answer is no. It doesn't. The idea is, as I mentioned earlier, is to augment human intelligence, to provide essentially tools to speed up and facilitate the process of scientific discovery. And indeed, Chris earlier was showing this example from COVID, from the COVID pandemic. the pandemic was really, I would say, a very important moment, because it really made it very clear to a lot of people, in particular to the scientific community, this issue about information overload, and how essentially our current technology is not yet up to speed to handle situations like COVID, when you basically get this huge collaborative effort of so many people working on the same in the same domain, producing a variety of results and a variety of publications in a very, very short time. I mean, the response from the academic community was really amazing. But at the same time, it was very, very difficult to for people to keep up with essentially this information overload. So essentially, what we need to do is to produce technologies that support scientists in their work. But I don't think nobody's really envisaging that AI will replace scientists for a number of reasons, including ethical reasons, but there are also more important reasons that at the end of the day, you need scientists to make key decisions about which avenues are more promising, which are less promising, where the money should be spent, etc., etc. That's not necessarily a decision that you can leave to AI, but AI can support the decision-making process.
Yeah, absolutely. And you've touched on something that I think is a topic here, because the next question we have: what can we do to ensure that AI is used ethically and responsibly in knowledge discovery?
Again, should I go ahead?
Yep.
Yeah, I mean, this is a extremely important issue, indeed, not just for knowledge discovery, but for the variety of applications of AI. I think, and indeed, we can say even beyond AI, the entire technological landscape, social media companies have been under fire for allowing this information to spread. They've been threat to democracies caused by the spread of this information. So to me, the answer is legislation. And I think it's good to see that the European Union is really leading the way with the EU initiative in AI and also the Digital Services Act. And they are producing reasonably granular frameworks to characterize AI applications and distinguish between applications that are high risk, low risk, and applications indeed that are simply not acceptable, domains where AI should not be used. And I think that's really crucial that this happens, and hopefully other parts of the world will follow very soon.
I think, yeah, and as we mentioned in the webinar, a critical part of that is making sure that the systems are, the output is traceable, and that which, brings back to that last point we were talking about, right? Hybrid AI systems and how, they are part of that solution there to help AI systems be more traceable.
Absolutely, yeah.
We have a question here. How does OpenAI or ChatGPT compare to IBM Watson?
This is a good question. I'm not really familiar with the very latest development of IBM Watson, also because IBM tend to essentially advertise their products once they're finished. So they tend to be a little bit more secretive than other companies about the things under development. So I would imagine that, of course, IBM is also working on generative AI as much as OpenAI. Certainly, I would say the traditional version of IBM Watson was not based on generative AI, but was really a collection of different modules, including a variety of machine learning modules, a variety of information extraction modules to, for example, to extract knowledge from text, but also I would say good old-fashioned knowledge-based systems of the kind of I used to work in the good old days. So as I said, it's difficult to know where IBM Watson is going, but if we compare the latest version of tools like ChatGPT with, for example, the IBM Watson used against Gary Kasparov, in the the one used after Deep Blue in, for example, in the quiz challenge, and also they've been working on cancer. They've been working on argumentation. The technology, I think, the underlying technology is a little bit different as far as I know.
Yeah, I guess I would guess, but yeah, I guess they would be also looking at, actually, as we were describing, combining, a ChatGPT type system with IBM Watson, most likely to further enhance, rather than expecting ChatGPT to replace what they have created completely.
Wonderful. When ChatGPT is used, what is traced or tracked from the user, and who holds this information?
I'm not sure if I have that answer. Do you know, Enrico?
Well, I guess they need to ask OpenAI. I mean, it's a very good question. Certainly holds this information. Obviously, the OpenAI servers all this information. I'm not familiar enough with terms of use to know exactly what this information is used for, but it is exactly the reason why these technologies need to be regulated. And indeed, to their credit, the OpenAI people themselves are actually calling for regulations, because they realize they are sort of their technologies are obviously breakthroughs in this AI. They're opening up new challenges, new opportunities, but also new threats and new challenges. And I think they understand that they need to operate in a world which is probably regulated, and where these questions are answered precisely.
Yeah, and I just asked ChatGPT, and it says that it's supposed to respect privacy. Its primary function is provide information, not collect information. It can only analyze data that if you give it personal data, you might include it in an output, but it's not collecting that information. And it should be respecting privacy and confidentiality.
That's good to hear.
Yes. Here we have another question. Does Article Galaxy or Research Solutions expect to incorporate any of these technologies in their products?
Yeah, so I think also you mentioned it briefly before the Q&A. So we're already testing within Article Galaxy a beta version where we have incorporated ChatGPT for a few well-defined questions, like frequently asked types of questions around finding content, and about the type of content, and about the authors of content that we have in Article Galaxy. So yeah, we've already been including ChatGPT, but we also expect to be developing other technologies, especially leveraging ontologies and knowledge graphs in enhancing the search experience within Article Galaxy in the near future.
Excellent. And could be related, another great question came in. How can a researcher start to integrate AI into their research process?
So, until very recently, that was really the domain of data scientists, who really could create or leverage these types of AI technologies. I think ChatGPT really now kind of democratizes that ability to somewhat. So, already, everyone now can use a very powerful AI system to help them and really speed up their work. Of course, there's the caveats that we've been mentioning in terms of the limitations of these systems, but also we've shown how potentially these can be improved. Ultimately, building robust knowledge discovery systems does still require the expertise of data scientists and specialists in AI. But yeah, there are more and more products coming out in just the last year. There's a huge number of new solutions coming out, especially also leveraging generative AI. So there's a lot of tools out there which are increasingly accessible for everybody to try out.
Wonderful. And we have, I know we're kind of coming up on time, but we have another question here. What is an ontology, and are taxonomies different?
One for you, Enrico.
Yes, I guess that's what we. So basically, an ontology is a sort of what technically is called a specification or an agreement. Essentially, if you have two computer systems that want to exchange information about the same domain, for example, if you're talking about medical diagnosis, then it makes sense to create a specification of the kind of concepts that these systems need to exchange, so that then this interoperability becomes possible. So an ontology can be seen simply as a database schema, except of course when you talk about AI system, typically it's not just a matter of exchanging concepts, but also relations. So the ontology is a way to more precisely, more formally specify these kind of data that systems can agree. So there is something called schema.org, for example, which is an ontology which has been defined collaboratively by all the top search engines in the world, like Bing and Yahoo and Google. And basically, what they do, in the schema.org, they provide pretty good specification of the kind of concepts, for example, that you might want to have in your website. For example, if you have a music shop and you want to sell record, you can put your catalog of records on the website in such a way that complies with the schema.org, so that then the search engines not only can access, get to their website and can index your website, but they know exactly what kind of products you are providing. And there are many examples in so many different domains. So the other point was the difference between ontology and taxonomy. A taxonomy can be seen as a very simple form of ontology, in which you only define the concept and the hierarchical links between the concepts.
Great, thank you.
Wonderful. And we are at time, so we will wrap here. Thank you everyone for your thoughtful inquiries. If we did not get to your inquiry, please feel free to reach out to us and we're happy to connect. But that being said, thank you so much to everybody for joining us today. And we're so happy and excited that we got to learn quite a bit about AI. And thank you again to our panelists.
Thank you.
Thank you very much.
Thank you, everyone. Have an amazing rest of your day.
Thanks a lot.